Well, hi, and thanks for joining me here in my shop. I finally obtained the new wire wound rheostat I need to replace this one with. Excellent. I checked this out on my own meter. It's perfect. This is NOS. It's new old stock. Feels fantastic inside too. So the name of the game is to get this control out, this one in. Part of that is going to be trimming the shaft here, which is much too long, and then it's a question of the final calibration and check through of this machine. I think I'm done at that point. So let's start on this right away here. Tight. There we go. When you use one of these tools, like you just saw me do, down like this, there's a chance these bottom edges will score the surface of whatever it is you're working above. If you're going to try that with something like this, you need to be really careful about not scratching up the surface. Now in this case, if I did scratch it, it's hidden anyway because the knob is on top, but in other cases that's not the way it is. Okay, let's go under here. So this is the guy here. Just gonna nip off these wires here. Hopefully they'll stay in their relative positions. And I have to put in wire extensions to get out with the old. USA patented. Okay. So what I'm going to have to do now is take the replacement. It's almost identical in size. A little different in terms of depth there. I've got to cut the shaft off to match this one. The threaded part's a little bit higher. I need enough shaft here to put the knob on. Cut it just a little long. I can always cut it again, that's the thing. I can always cut it shorter. It's about that upper line's about correct. Now how am I going to cut this? I don't want to, if I wail away with a hacksaw, I'm shaking the living daylights out of it. It's just going to shake the heck out of it. It's going to transmit all that vibration right into it. I could cut it with a Dremel. This feels pretty hard. I think it's a hacksaw. Okay, let me get ready for that. Okay, so I'm thinking on the vibration concern, whether it's real or not. Put it in a big vise, clamp it really hard. That's going to suppress the vibrations a fair bit. There we go. So it's just a question of hacksawing through it. Now let's take another look here just before I boob this up. Wonder how close we can get at this. Get a look at this. Why not? It's going to shake my camera. Why not give it a try? A little bit of sanding's in order. that's it. Very good. There's no doubt I gotta get a new vacuum cleaner. Every time I use that one, I smell smoke in here. The smoke is bad. Ooh, really bad. I think that's gonna go on fire next time I go to use it. Okay. Now we need to install this guy. Oh wow, it's really smoky in here. Maybe that's the last time I'm going to use that vacuum. Yeah, I'm going to part ways for a minute here and let the air clear in my shop because it's too smoky. Okay, the locking washer there. Goes in just fine. The wires might be a little short. Make sure I put this in perfectly straight because there's a calibrated dial markings on the other side. Okay. Let's see if I can tip this up on its side here. That's pretty good. I should put a lock under this. A lock washer. There wasn't one there. Basically, if this, what I'm putting in can't move, if it's locked in place, then this should never loosen off either. I guess that's the idea. Okay, right there, without moving. Okay. Now the lock washer should hold the control in place while I tighten this. It's not moving at all. This is where you can really easily scratch, put a huge scratch into something. Tightening up, you're drawing the tool down closer as you tighten the nut, and because of the power you're putting in it, you can't feel the fact that you're digging a groove in the front of the panel. So it's all about looking at what you're doing here. And a fairly powerful tool here too. There we are. I think that's tight. Okay. Wonderful. Okay, let's put the next step. I guess we'll put the wires onto it. This has a fairly flimsy front panel, thin sheet panel here, and if I pick it up by the corners, it's going to flex a lot. I'm trying to avoid that by picking it up by, you know, this part here, the more rigid parts and that. Just let you know what's going on. Now, so I have a capacitor that I replaced back here, and I did it with an NOS capacitor, and I'm going to replace it again with a brand new one since I have them now in stock. Because I'm just worried, although this capacitor tested fine, I'm just guessing if there were a short in this capacitor that could allow a heavy current to flow through this control, and that may be what killed the original one, that exact problem. Now, I did take out the old capacitor and test it. It didn't test that badly, so you know, it just stands as nothing more than a theory as to what happens to the other control, but I certainly don't want to take a risk with this one. Can't remember the size of the capacitor. Snip it out here. /30. You look on the schematic and try to find the value on the schematic here. Okay, so I'm installing a new 2 microfarad capacitor here. Get rid of this one, which I'm just not sure about. And what I've noticed, oh my gosh, the terminals, which are screwed to this one is loose anyway. Oh good, it's only one. Because how am I going to get a screwdriver in there to tighten up the little screw at this point? So I should have checked that before I put it in. Screw is practically falling out. Screws tight. Screws tight too. So just one was loose. Screw. Good. Okay. I thought that was in that. I thought that was going to be a disaster. Now, I'm going to attach this wire here. So I have been giving a lot of thought to vacuum tubes and tube testers, and getting a lot of experience here and reading a fair bit of stuff. And all that combined has opened my eyes to one big factor about tube testers that doesn't seem to be written anywhere. Clearly, anyway. So my imagination has told me that the way these machines work is they set up a test scenario based on plate voltage, screen voltage, all that stuff, grid voltage, everything. And then if they're a mutual conductance tester or a GM tester, then they apply an AC signal to the grid and they watch the variation in the output, and somehow they mathematically calculate these things together inside here. Calculate's a strong word. The two factors are used to resolve some meter movement on the front manometer. What I've realized is the voltages that they're putting on the tube under test are nothing like what we would find in a radio. For instance, in a radio you'd find a steady state B plus DC voltage on the plate. But in these testers, you're liable to find some sloppy AC thing on the plate. Likewise on the grid and the screen. So in a sense, where you might have 3 steady state voltages in a classic laboratory kind of test of a tube, in these testers you've got 3 things going all over the place. Maybe not relative to each other, they're all going together, so the relative effect is the very same as having 3 solid ones. That's one thing. These do not test tubes in a simple under simple circumstances, let's put it that way. I suspect what they do with these machines is they try to build them to be as linear as possible. This is what I suspect. See if I can pull enough slack out of that wire. So that the linearity of the device allows them to make selections on the settings based on data they find about the tube they're interested in. So if you're going to look at a tube manual, like when in the factory where they're building these or designing them, they look in a tube manual, look at the statistics for a certain tube, and there isn't one set of statistics either, right? They usually give 2 or 3 sets of different plate voltages and that, or they give up on that and just give you a graph because the situation is complicated. There's too many varying factors simultaneously to make it simple to understand. If you think they're looking at that kind of information and then deriving what the settings should be here, and I'm not talking about the selecting plate, cathode, I mean that's obviously almost mechanical, selecting the right pins to fire voltages onto. It's the level of those voltages and the kind of voltages that is not at all what I would have expected. In my imagination, I thought I'd be able to plug a tube in here, set the dials, and then know the tube has got a B plus of 250 and the bias is so much and the screen voltage is so much. I think in the end, what they're doing with these, and I'm not sure, maybe the different factories and different designers did different things, but at some point I almost think they were putting the tubes in to test, setting the machine up roughly, and then looking at it and saying, okay, so this is a good tube, the GM should be 3000, and then they adjust the bias control until they see 3000, then they go, there, write down that bias number, because that's the number we want everybody to use on this tube to get that reading. I think that's what's going on with these. I don't think it's as scientific as we might want to think. So, sorry I stopped working there while I was talking. So, in thinking about that, I would love to have, quote, a standard tube, which apparently was a common thing back then, that you would put in your tube tester, and with the standard tube you could verify or calibrate your tube tester. Well, who's got a standard tube? Who would even know if their standard tube was still standard? Would they pull out their bad tube tester and check the bad standard tube with a bad tube tester? Or like me, get 3 tube testers, they all say different things? You're still left wondering what is going on? This one I was able to get slack, so that'll fit in there nicely. Now this other one, let me get a stronger plier and show it who's boss. There, hey, I like that, a whole bunch of slack, fantastic. So my thinking is this: I need a standard tube. To get a standard tube, or a tube whose factors I know without doubt, I need to test the tube myself outside of all these tube testers by doing that standard thing of applying controlled B plus at a known level, all that stuff, set all that up using shop instruments, not using one of these, and then actually do a real sort of laboratory test on a tube to derive its true GM or other operating factors that might be revealed tube test. Actually, GM is really the only one I can do. On the emissions side, there is no such thing as a scientifically done emissions test. There is no emissions number. The manufacturers don't quote one. So, and if you look at the face of the meter, it's just, you know, good and bad, and good and bad actually the other way. It's not. There's no. It's hardly a quantitative test. So I'm thinking there, what they do is they either again by using charts and graphs and calculations and numbers, they figure out what the settings should be on here because there's 1,000 tubes, you know. Or, believe it or not, they've acquired maybe the 1,000 tubes, or they've acquired a certain set of tubes that they think are good enough for them to calibrate this. They put the tube in, they believe it's a good tube, and they make adjustments to make the meter go up into the good range, and then they record the adjustments and put it in on the roll chart. Then I come along, mimic those adjustments to get that same reading, unless the tube is bad. And that's what I think is going on with these. I don't think it's as engineered or scientific as we might think, or mathematical maybe is the right word for it. So I think this is all my imagination based on everything I've done here. The manufacturers are not going to reveal anywhere, I think, their deeper concerns about tube testing and that. I mean, they were making products to sell. They weren't making products to tickle the fancy of scientists in laboratories. They were making products to sell to guys who were going to show up in your home in front of your black and white TV. That's no longer black and white, it's just black. And I would think if you showed up in somebody's house, and almost any TV repairman back in the 60s could do this, look at the TV set and deduce what tube was shot in it pretty quick. And it was always the same tubes. Same thing in radios. The hard working output tubes, the ones with a lot of power, are the ones that wear out. So horizontal output tube, it's pretty quick to figure out what's going on. So you come in, you announce to the guy, oh, it's your horizontal output tube. You pull the tube out, you're about to put the other tube in, and the guy says, wait a minute, you're spoofing me. That tube's not the problem. You don't need to change that tube. And that's when you pull out your tube tester. The eyes pop out of your customer's head as he watches you deftly work all the controls. Push the button and the meter says, bad! Now you're going to sell that tube. Yeah, so maybe that's part of it is, I mean, maybe even repairmen were being asked, well, do you have a tube tester? No, I don't. Oh, well, maybe I'm going to get another guy. I don't know. You had to lay out a fair bit of money to get a tube tester as a repairman. It's quite a chunk of money. Slow right down when I start talking like that. There. But somehow I've managed to make all the connections. Excellent. Let's solder him up. This guy's ready to go. Was there something else I was going to do in here that I've forgotten about? I don't think so. How do you know if you've forgotten something? Checklist. That's the only way. we are. That is done. That's a little better. Okay, let's flip it over. Trickier said than done. Just cut my hand right through there. Can you believe that? Cut my hand on the corner of this. Son of a gun. Right where you, who wants to cut your hand there, for crying out loud? Yeah. Okay, I'm gonna go take a break for a little bit and let that sort of start the healing process. When I come back, we'll get this guy. Well, we should give him a test on a tube, I guess. A test on a tube. Sounds good. Okay, I have to go and bleed for a while now. Okay, put the knob on here. Let's turn this all the way to. It's there. Now, when you're doing an emissivity test, this scale out here is critical. You set this according to the scale. So, oh, I set it for the 50, but it doesn't come to the 0. What's better to set it to? The 0, I guess. I don't know. Or set it in the middle. Again, as I was saying, the emissivity test has a little bit of jokiness about it. So, you know, how much precision I need on these things, really. Kidding myself. Okay, we're ready for a tube test. Tube we're going to test to be a 6F6. Was that? No, 50L6 was the last. 6F6. I think I gotta look this up on the computer. That's the problem with these roll charts. It's not going to show up. Okay, let me get it all set up and away we go. Okay, let's set it up. 6F6, I'm looking at the chart here. 6.3, correct. CGGG dash. CGG G, and this doesn't matter. 26431. 2, 6, 4, 3, 1. 0520, 0520, 0. 05200. 1.7 on the bias when we get around to it. 1650 shorts on 2 and 7. We should see shorts on 2 and 7. Okay, we're ready to go. Test position. Test position. Okay. See if I can remember how to do this. Let's plug it in. Okay, starting first with the dim lights. Okay, everything looks pretty good so far. Okay, that's full power on it. Line adjust without the tube first. Touch high, pop the tube in. Oh, what to do about these? These current guys. This is, I have this off here to run the filament current through it. It's not supposed to go in there. I thought those were supposed to go in. No. Okay, so I can either put a meter on this. I don't really feel I need to, or just short them. I like to short them in some. It's carrying current. Yeah, best thing to short it with is an ammeter. Okay, we'll do that. Apparently we won't do it with this one. Yeah. Despite all its warnings, the batteries have gone dead in it. Oh, son of a gun. Well, okay, I gotta ponder what I'm gonna do here for a sec. Ponder. A big fat clip lead. Let's try that. The big fat clip lead solution. Big fat leads. Eventually I'll probably remove these from the oh, it's not a clip lead. Wait a minute. No. I thought I grabbed a clip lead, but I didn't actually grab a clip lead. Let's try it again. Let's try this. Yeah. So that can probably carry the current involved, which we can of course check on the meter because this guy has that ability. Okay, where are we at? So the switch is on. Everything's ready to go. The line was testing. Is still testing just above. Put it on to short 1. The reason for that is it breaks the heater current. So rather than have it on test, plug in the tube, start heating it, then move it to short, I'm just going to avoid one heating cycle in it. It's the heating cycles that probably wear tubes out. We should see a short in 2 and 7. 2, yep. 7, those are the heater terminals. No shorts anywhere else. We put it in test mode and I saw the light dim, and that's the heaters being kicked back in. We'll now check for the bias setting. The bias setting is supposed to be 1, 1.7, I think. Let me just check. 1.7. So we set the bias. Notice it's all working really nicely. I'm happy now. We're on the 10 scale. 1.7 way down here. Right around there. Bias set. Yeah. Yeah, 1.7. From here we go to line test. Just make absolutely sure the line is right on the money, because there's nothing precise about what I'm doing anyway, but how much fun it is to fool yourself into thinking you're doing something. You're not. 1.6. Well, let's just be precise there. We are 1.7. We're now in test mode. When we test it, we should get a reading of better than 1650. So 1650 on the C scale. They don't actually put the letters up here. So it's on the 8K scale. 8 on the 8. Yeah, 8K scale. Plate shunt. So, I was thinking that it says plate shunt and then it says 8K, 20K, 30K. I thought that was the actual resistance we're switching into. But it's not. It's the name of the scale up here, I believe. So we're on the 8. So if we're on the 8 scale and we're supposed to get 1650, it's way down here. Right around here. Ready on the test. Right there. The actual reading there would be on the 8 scale 1000, 1008, about 1850 instead of 1650. Well, I think that shows that the machine is working. Now, whether it's working properly, calibrated, all that kind of stuff, it's my next approach on this. Is to run quickly through the alignment calibration process, and then it's to attend to the problem of getting a standard tube. I still got to think a little more about how I want to approach that, but then once I have a tube whose GM I know for sure, I can put it in this machine and my other two tube testers that can read GM, and see, and we'll see. Boy, will we ever see. So thanks a lot for watching, and you know what? I still have some more tests to learn in here. Gas test. Why don't we do that? Let's do that now. I got a gas test here, so I'm going to read up on it, and we'll perform the gas test on here, and we'll see. Okay, here we go. Let's test for gas. So what's it say here? Gas current is actually a reverse current through the tube. It is particularly noticeable when the grid of the tube is biased highly negative. Gas ions then flow to the grid, causing it to become less negative. That's quite interesting. Now, gas ions are positive. You know, the electron's been stripped off them, so they're positive, and that's why they're attracted to the highly negative grid, if the grid is highly negative. So that's the problem, a current flow onto the grid. To check the average tube for gas. By the way, I have this switched on. Now you'll see why in a moment. It's just sitting here on. Set it to the GM test and then proceed as follows. So this is set to the GM test. So I'm going to proceed as follows. Rotate screen voltage switch to A. This lowers the screen voltage. Screen voltage here to A. Lowers the screen voltage. Set bias slide switch to 50. Set the meter switch to test. So this is the meter switch to test. Adjust the bias potentiometer until the meter just barely reads on the scale. About a quarter to a half inch from the zero is about right. Well, that's a little more than just barely. Uh-oh. Is this supposed to be is the test button supposed to be in test? That's this one way down here. Rotate this lower screen voltage. Set bias slide switch to 50. Meter switch to test. Well, I got the meter switch on test. But I don't have the test switch on test. Is there something wrong here with the instructions? If the meter switch is on test, but the test switch is on off, then how can there be anything going to that meter? What am I reading wrong here? Set the bias slide switch to 50, the meter switch to test. Adjust the bias potentiometer until the meter just barely reads on the scale. Push the gas test switch. It never ever says put the meter into test mode. Or did I miss that up above? Did I miss that up above? So maybe what they're saying, is that it says set it for the GM test. Okay, so right now with my test switch set off, it is not set to the GM test. It is set to off. So maybe I should set it to test here because of this statement. So let's try that. Okay, let's try that. So this would go back to G, if I'm going to follow the instructions verbatim, which I'm going to. Rotate screen voltage switch to A. Okay, I just lowers the screen voltage. Adjust the bias potentiometer to the. Oh yeah, I was going to have this on test. Oh, test hold. I don't know. Adjust bias potentiometer until it just barely reads. There we are. Now we're cooking. So maybe there's a problem with the instructions there, or the assumption is you've left it in test mode from the last test. Okay, so we have it just barely up. That's, what, quarter inch where? Quarter inch at the very, very tip, I suppose. Now, quickly, next thing. About right. Push the gas switch if the meter moves more than 1/16 of an inch upward. Here we go, gas test. Oh, let's watch the meter really carefully here because you can't see it in a longer shot. Let's get a good look at it here. Let's try to get a good look at it anyway. That's not too bad, we'll leave it like that. He says immediately moving it. That's not too bad. Okay. Question is that meter going to move upwards when I push this switch here? Try my best not to shake anything. See if I do this. Let me put the brake on it because I know for sure I'm going to shake it. I'm looking for a 1/16 of an inch. Okay. Everybody watch it. Here we go. Well, I don't see any movement, or a ever so tiny movement downwards. I'd say no movement. So, until I get a gassy tube, really, gassy tube would be a real old one. That's the word. The word on the street is, once you get to these, this type of tube with the octal base and that, the gas leak problems were pretty much solved in these tubes. You need to go back to the 30s or even earlier. Where the gas leak problem had not been solved. So there was a slow rate of gas. Maybe we should try one more. Let's see if I can find a gassy looking tube. Let me look through my stuff and see if I can find a sick puppy here. Okay, so I have a couple of older tubes here. You can see the type of tube base. Oh, here comes my cat Peanut. But I thought I'd show you this one. I won't be testing this one. This tube is a WD-11. This is the first commercially available tube on the market, as far as I understand it. This is the granddaddy of commercial tubes. This was quickly replaced by a WD-12. So this was on the market for about 6 months in 1921, 22. So this is, for tube collectors, this is the tube. This is one of the tubes you want to have. I got one, but I'm not going to try and test it. Now, my poor cat, it sounds like he's dying out here. What is it? Is that so? You're going to come in? Coming in today is the same thing every day with you, isn't it? Apparently he wants some attention. Probably wants me to go upstairs. Let's leave this one out of it because it has a grid cap right now. We're going to leave that one aside. I'm going to take this as a number 27. A number 27. That's a really old tube. It says on a 1923, 1940, so we know this was made after 1940 anyway. That's surprising to me. It must have been making tubes which were no longer going into new equipment, but was going into to replace tubes in the older equipment. So they must obviously keep making parts for the old radios. So I need to set up for the GM test on a number 27. Oh my gosh, would you believe it? It's right. I just happen to have this roll chart turned to 27. It's right there. Okay, let's set it up. 2.5 volts on the heater. CGGG. CGGG. 64125. 64125. Just think, I thought this tube tester was a piece of junk too. The next row is zeros all the way across. Nada. 0, 0, 0. The bias is set to 10 volts. The GM should be 650. Shorts on 1 and 5. Okay, let's just review this because this is an old tube and I don't want to damage it. 2.5 for sure, that's correct. CGGG. CGGG. G, yeah. Control's unimportant at this point. 64125. 64125. Pile of zeros. 10 volts on the bias. Put it on a 10 volt scale and go for full scale. 650, 1 and 5 on the shorts. Now, why have I got this down? I've got this down here because you're supposed to be looking at this down there. Okay, goes right into this socket here. I'm going to watch the light, see if it dims. The short light has come on. Short light has come on. Oh, I have a short position number 1. Position, and the shorts are supposed to come on in position 1 and 5. No problem. Put her back in there. Remember, the heaters, if this is in a short position, there's no heater energy supplied to the tube. So I believe. So short in 1 is fine. 2. The other one is 5, I think. Yeah, 5. Short there, yep. Those are probably the heater pins. No shorts coming up. Line check. Good. Bias set to 10. 10 is full scale. Yikes. We're going to get there? We're not going to get there. Now this is where I think you can burn this control out. When you get close to the limits and there's only a little bit of wire involved, I think if the circumstances are bad, that little piece of wire can get very hot. Okay, so there's quite a bit of heat coming out of this one down here, the line adjust. Is there any heat at all in the... I don't think so. Well, we're not going to get this up to 10. Let's put this on the 50 scale. Maybe that'll help get to 10 that way. Okay, on the 50 scale, we're getting a totally different reading, I think. Okay, so you're changing more than just the range of the meter when you throw the switch. You're also changing the amount of voltage you get out of this guy. That's what's going on. So now we're on 10. We're ready for the test. Over to the test. Oh, get it on camera. So this tube should test at 650. We're on the 8K scale. 650 is just up a little bit. It's below though. It's right around where my finger is. Really? Yep. That's where it's come up. So this tab, what I would say from this test is this tube is good, regardless of what the reading is. Now we'll take a look for the gas test process. We've just checked it for GM. I'm going to put the GM test on. Hold. We are now going to flip the screen voltage down to setting A. Is that right? And proceed as follows. Screen voltage to A. Lowers the screen voltage. Bias slide switch to 50. Meter to test. Oh, okay. It's on 50. Meter switch to test, it is. Adjust bias potentiometer until meter just barely reads. It's almost there now. Okay, so there, it's just barely reading. And that's it. Now it's a question of pushing the button. It's got to be good enough like that. Let's check and see. There we are. Watching that meter. Will it move? Here we go. Gas test. I don't see any movement whatsoever. No movement. Test off. Test back to G. Tube out. Wait a minute. Heater off. Tube out. My tube collection totals about 1,000 tubes. About 500 of them are useful radio tubes of some sort. The rest are TV tubes and who knows what else. If I were to take those 500 tubes and apply a really careful test to them and do it on a couple of testers, that would be roughly, probably, making notes and just everything involved in doing that, organizing the tubes, all that stuff is probably in the range of 10 minutes per tube. That would be 5,000 minutes. That's a lot of time. So that's what's in the back of my head here. How am I going to get through hundreds and hundreds of tubes if I care to test them? With 3 testers, multiply the whole thing by 3. So I think we're going to stop at this point. I think I have enough experience now on this tube tester. Really, I'll keep my eyes peeled for a tube that I know has air in it because of the getter going white. If I can find one of those, we'll stick it in here, and that would be an egregious amount of gas in the tube. Egregious. But then it'll give us a chance to do the gas test and see if it really works. I have another tester that does a gas test. This one also does a noise test, by the way. You can see these outputs right here. And I have another tester that has a noise test on it. Excellent. Wow. Okay. Fantastic. What about the calibration of that? Right. Forgot about that. Okay, we'll see you on the next video. Calibration or not.